Hello and welcome back to another Physical Sciences 3 lecture. We are looking at example 14 in the electrical power section, and this is on page 27. Okay, so in this example we have a 1 kilowatt mains heater runs for 1 hour. So just remembering that's going to be P. Mains indicates that V is equal to 240 volts. We might not need that this time, but just a good reminder. And 1 hour is equal to 3,600 seconds. Okay, that's time equals 3,600 seconds at 60 times 60. How much heat energy in joules does the heater emit in this time? So if we look up ahead at the previous page and we look at this equation here, so power is equal to the change in energy over time, we have power equals change in energy over time, and that means that the change in energy is equal to power times time. And we have 1 kilowatt, so it's 1,000 times by 3,600 seconds, and so that's equal to 3.6 times 10 to the 6 joules. And just remember you can write that as 3.6 megajoules as well. Okay, so that 10 times 10 to the 6 is a mega. How much electrical energy was used? So heaters emit heat, so they emit heat, and as we saw with mechanical energy, often heat is a byproduct, something we don't want, but obviously when we want to heat something up, heat is what we do want. So it means that heaters are 100% efficient. Well, they should be. Heaters are 100% efficient, therefore 3.6 megajoules of electrical energy was used. Okay, here's 100% efficient, therefore 3.6 megajoules of electrical energy was used. If the whole generation and distribution process in hydro generation is 65% efficient, how much potential energy due to the water was used? Okay, so just a quick note, we've got a little picture of a dam down here. If you're not sure about the the hydroelectric process, essentially what happens is the water has a potential energy, it's up very high, so water has an EP equals to mgh, and as h becomes less, goes towards zero, we convert that energy into electrical energy. So it spins turbines, so the EK spins the turbines, so the kinetic energy I should say, spins the turbines, and then we can use that that kinetic energy from the turbines, we convert that to electrical energy. Okay, so and you can encourage you to look up videos or whatever on YouTube if you can find some to explain the hydroelectric generation process. But if the whole generation and distribution process in hydro generation is 65% efficient, how much potential energy due to the water was used? Okay, so what we actually need to do is the energy will be equal to energy used divided by efficiency. And we could say that's total energy here. Total energy is equal to energy used divided by efficiency. So it's 3.6 times 10 to the 6 divided by 0.65. And if we look at that, let's put that into our calculator. So okay, so we end up getting 5.54 megajoules, or 5.54 times 10 to the 6 joules. All right. So the final question here is if the dam in question has a head of 35 meters, so if it's 35 meters tall, and my robot vacuum cleaner is just trying to come in, I'm going to turn that off for a second. excuse that break. So, robot vacuum cleaner using up some energy in the room. Made a bit noisy. And anyway, if the dam in question has a head of 35 meters, that means if this is 35 meters tall, how much potential energy does the water have? And remember that 1 liter of water is equal to 1 kilogram. Okay, so then what we will say is that our EP is equal to mgh like normal, and that means that we're looking for the mass. It's equal to G times H. We got EP is equal to 5.54 times 10 to the 6, and we're dividing that by 9.81 times by 35. Okay, and so making sure that we put our brackets in the right place, I'm going to put brackets around the top ones. 5.54 times 10 to the 6. It's our first bracket, divided by 9.81 times by 35. And so what we get is 16,000 litres. So about 16,100 litres. Or 16,000. We'll just say 16,000 litres to two significant figures. 16,000 litres to two significant figures. Okay, great. And yeah, we're going to look at household electricity next.